Hello, welcome back again to the channel. On this video, we are going to discuss the invertibility of a diagonally dominant matrix. So first, we start with a definition. So definition, a matrix A. This can be a complex entries matrix, is called a diagonally dominant matrix if for every I equals 1 to up to n, for each row the diagonal entry is the modulus of the diagonal entry is much bigger than the sum of the modulus of the rest entry. So the modulus of AII is greater than the sum of all the other modulus on the same row. Okay, so example, let's say we have 5 1 plus I yeah. So the modulus of this is square root of 2 plus 1 is still bigger than 5. Let's say 3 0 2 6 2 plus I. That's gonna be square root of 5. Square root of 5 plus square root of plus how much is less than square root of 5 is 2 point something, less than 3. So like this. This is a diagonally dominant matrix since for each row, so let's consider this row, 5 is bigger than 1 plus I plus 1, which is square root of 2 plus 1, right? And then here 3 is bigger than 0 plus 2, and the last one, so that's the 5, that's the 3, and that's the 6, and 6 is bigger than, which is square root of 5 plus 2, right? Okay, now one of the main advantage of having a diagonally dominant matrix is that for sure we know that every diagonally dominant matrix is invertible. So theorem, I think this theorem is by Levy. I hope I write the name correctly. every diagonally dominant matrix is invertible. Okay, we prove this statement. So proof. So we will argue by contradiction. Suppose on the contrary that so let's give a name to this matrix as A. Suppose on the contrary A is not invertible. Right? Then there is X in Cn. So let's A is a complex entry matrix, X non-zero, such that AX equal to 0. So remember that one of the criteria of invertibility is that an invertible matrix has only a trivial solution to the equation AX equal to 0. So if A is not invertible, then therefore there is a non-zero vector X such that AX is equal to 0. Okay, so now suppose so since X is not 0, then there is an entry of X which is not equal to 0. In particular, we can compare the moduli of each of the component of X, and we can take the component with the biggest modulus. So let's call that X sub k is the entry, the component of X with the biggest modulus. So this is the maximum of xi, right? Okay, now we look at the kth component of AX. Consider the kth component of AX, which means we multiply the kth row of A with the vector X. So we have the sum of AK. So we don't write it explicitly that the entries of A is Aij. So AKI times XI, where I runs from 1 up to n. Okay? Then certainly the kth component of AX is also equal to 0 because AX is a 0 vector. So this is equal to 0. Now we will separate the term where I equals to k and the terms where I is not equal to k. So if we isolate when I equals to k, we have AKK plus AKK XK. So plus the remaining terms, but we will move away the terms to the right hand side. So it is equal to negative j is not equal to k, akj x j, right? Now take the modulus of both sides of the equation. So we have akk xk is equal to the modulus of the sum. So when we take the modulus, the negative sign is disappear. So j is not equal to k akj xj. Okay, by the triangle inequality, this expression is less or equal to the sum of the modulus of each terms. So akj xj. Now, since the modulus of xk is not equal to 0, we can divide both sides by the modulus of xk. So we have akk is less or equal to the sum of j is not equal to k okay, now recall that the modulus of k is the biggest among all the modulus of xi. So therefore, this over this is less or equal to 1. So we have this equal to this less than. Now if we read from the left to right, it says that the modulus of the, so on the kth row, the modulus of the diagonal entry is smaller, is less or equal to the sum of the rest of the modulus. So it means that A is not diagonally dominant, which is a contradiction. Contradicting to the fact that A is diagonally dominant. So therefore, our assumption is false. A then must be invertible. Therefore, A is invertible. So then, a cool thing that we can have from this theorem, a matrix like this is invertible without us checking anything. We just check that for each row, the modulus of the diagonal entry is bigger than the sum of the modulus of the other entries on the same row. Okay, so that's all for today. Thank you for watching. See you again on the next video. Bye bye.